So welcome to today's central exercise session. As usual, you're welcome to ask questions that you have during the session on chat. We have a channel on chat.tum.de, so please log in there if you haven't done so yet. And the channel that we monitor during the central exercise session is this one, MA9711-CE for central exercises. The chat will be moderated as usual. And before we start, I'd like to invite Lesuri, our moderator, to briefly introduce yourself.
Yeah, hello everybody, and welcome from my side as well to the central exercises. Well, you might know me from last week. I'm a researcher and teaching assistant at the chair of math finance at TU Munich. And I will be happy to get your questions, answer as much as I can in the chat. And the ones that they require a lengthier explanation, I will take them and bring them to Professor Ritter later on.
Okay, thanks a lot. So before we start, a brief announcement. We'll take a quick break at around 2 o'clock for the election of the semester speakers. And at that point, I'm going to give over the moderation to a member of your student council who will then join us. So let's have a look at exercise sheet number 3 together. That's today's exercise sheet. So the topics of that sheet are mainly linear subspaces. That's the first problem. Then we'll discuss linear independence. We'll discuss linear combinations, bases, and dimension. Those are the main topics of this exercise sheet. So let me start the screen sharing so that you can actually see what I'm doing. Good, I hope you're seeing my screen now. If not, please just post a message to chat. I just start with 3.1. 3.1 is about linear subspaces. So C3.1. And the task here is to check 2 different sets for being linear subspaces or not being linear subspaces of the vector space R2. So we have this larger space R2, we have a subset of R2. And remember, a linear subspace of a vector space is a subset that is in itself a vector space. And because a subset, of course, inherits all the nice properties from the surrounding space, there's not very much to this property. So being a subspace basically means the space is closed under the usual operations on vector spaces. So that means whenever I add 2 vectors from that set, I end up with a vector that is again in that set. And whenever I scale a vector, so multiply a vector by a scalar, I again end up with a result that is in that set. So I don't leave the set if I'm doing any of the usual vector operations. And then all the nice vector space properties will just be inherited by the larger set. And we know that the space is a vector space. Okay, so basically those are the 2 points that we have to prove. One more thing we'll have to think of is the empty set does not make for a very good vector space. So we'll exclude that one. And that means we have to check whether our spaces or sets actually contain some elements, so they're not empty. Let's start with subproblem A right away. So here we have the set U1. U1 consists of all vectors x1, x2 in R2, where x1 plus 2x2 is equal to 0. So that's the definition of that subset. And the question is that a linear subspace or not? And the first thing that you usually do is you check whether your set is empty. So the question is U1 the empty set? And usually the easiest way to check that is to have a look at the 0 vector, because every vector space, and therefore every linear subspace, must contain a 0 vector. And that means we can just check if that is included in the set. If it's not, it cannot be a vector space. So it cannot be a linear subspace either. If the zero vector is included, we have found an element in that set, so it's not empty. So either way, we have either proven the first property, not being empty, or we have already found out that it cannot be a linear subspace anymore. One of these two things will happen. So let's try that. So the question that we ask here is the vector 0, 0, is that in U1? Well, U1 is defined by this property here. So U1 consists of all vectors that fulfill this. The first coordinate plus 2 times the second coordinate is 0. So what we have to do is we have to check whether this holds for the 0 vector. And that's what we're going to do. Well, the first coordinate of the 0 vector, the x1, is 0. The second coordinate is also 0. So we have 0 plus 2 times 0. Well, and of course, that is 0. So obviously, the 0 vector fulfills that property. And that means 0, 0 is contained in U1. And that means in particular, U1 is not the empty set. And that is what we wanted to show here. Okay, so that first property is usually easy. Now let's have a look at the other two properties. The second property of a linear subspace is that the sum of any two elements of that space is again contained in the space. So we take two arbitrary elements, let's say x and y, let those be in U1. And then we have to show that their sum is again in U1. We'll give that sum a name to make notation easier. We'll call that C. So C is x plus y. And we have to show that this is again contained in U1. So with x and 1 having components x1, x2, and y1, y2, you of course get that set with components C1 and C2 has C1 equal to x1 plus y1 and C2 equals to x2 plus y2. So again, we'll take a look at the defining property of that vector space here. And we'll need to prove that C fulfills this property. So the question is C in U1? Well, to check, we'll have to see whether C1 plus 2C2 is equal to 0. Let's do that. C1 plus 2C2, that is equal to, well, the first is x1 plus y1. The second is x2 plus y2, so 2 times x2 plus y2. And then we can just reformulate that a little. Let's collect all the x terms first. So we have x1 plus 2x2. And then we collect all the y terms. That's y1 plus 2y2. And we did that because we know that x and y are contained in the set U1. So as they are contained in U1, that means these two vectors fulfill this property. Otherwise, they couldn't be in U1. And you notice that this here is exactly the same as this left-hand side here. So as x and y are contained in U1, we know that this here is 0, and we know that this here is 0. Because x and y are contained in U1. And that means what we have here is 0 plus 0, and that of course is equal to 0. So obviously C has the right property. That's what we wanted to show, and that means C is contained in U1. So the sum of any two vectors, arbitrary vectors, is again in U1. And let's move on to part 3, which is almost the same thing. We now need to show that for any vector in U1, any lambda times that vector is also contained in U1. So we'll start with x in U1, and we'll take a scalar lambda in R, and we need to show that C equals, let's define that as lambda times x this time, that this is also in U1. Now we know C is again made up of the coordinates C1, C2. And obviously those are just lambda times x1 and lambda times x2. So again, we need to check the property of a vector space. Again, remember that was this property here. So the question is, does C fulfill that property? So we check whether C1 plus 2C2 equals 0. And let's just write that down. First coordinate is lambda x1. Second coordinate is lambda x2. So obviously we can factor out the lambda. That is lambda x1 plus 2x2. And now, very similar to what we had before, you'll notice that this part here, x1 plus 2x2, that's exactly what appeared in the definition of U1. So as x is in U1 by our assumption, that means this expression has to be equal to 0. And that means what we have here is lambda times 0. Now lambda is just a real number, and any real number times 0 will always be 0. So we have again seen that this expression here is equal to 0. And that means C is contained in U1. So we have shown that U1 is closed with respect to scalar multiplication, and it's closed with respect to vector addition, and it's not the empty set. And from those 3 points, we can easily conclude that U1 is a linear subspace of R2. Okay, let's see what questions do we have already.
So there is a question that it is asked whether it is possible to determine the basis of U1.
You want to determine the basis of U1. Can we postpone that a little? So maybe we can do this after 3.2. I just like to use 3.2 to talk about basis first, and then of course we can do that example as well.
Perfect.
Could you remind me later?
Yeah, I will.
Thanks.
And there is another one. Could we use concrete vectors instead of x and y in step 2?
Okay, so the question is, can we use concrete vectors in step 2 and probably also in step 3 instead of using x and y? And the answer is usually no. The idea here is you need to prove that this closedness, this here holds for every possible choice of x and y. And if you use any two selected vectors, then you're only proving that the sum of these two is again contained in the space. But what about others? So I could still give you a different vector and challenge you and ask you, well, what about this one? Is the sum of this and that one also contained in U1? Can you prove that? And usually the vector spaces we're looking at will contain an infinite number of vectors. So listing all possibilities is just not feasible. And that means you have to provide a general proof for that. So you need to assume arbitrary x and y. And in 3, you need to assume arbitrary x and arbitrary lambda. If you choose just some examples, then that doesn't prove it in general. What you can do, however, is you can use or you should use even actual numbers if you want to provide a counterexample. So if you want to show that a given set is not a linear subspace, then it's sufficient to exhibit one pair of vectors where their sum is not contained in that space anymore, because the property must hold for every pair of vectors. And if you just can find one where it doesn't work, then you're good. Then you have shown that it cannot hold for all. So in that case, for a counterexample, using actual numbers is fine, and even the preferred method. Whereas for proving that this property holds in general, you cannot usually do this using concrete numbers. Any other questions?
No, so far.
Not so far. Okay, good. Just one more thing I'd like to mention. You might have noticed here that in the definition, U1 is actually defined using a linear equation. So using all the facts that we know about solution sets of linear equations, that proof could have been much shorter. We could just have said U1 is a solution set of a linear equation. So it's the solution set of the system of linear equations x1 plus 2x2 equals 0. It's one equation, but still one equation is a system. One system, two variables. So U1 is a solution set. The right-hand side is 0, so that's a homogeneous SLE. And if you've paid attention to the videos, you will know that the solution space of a homogeneous SLE is always a linear subspace of R to the n, where n is the number of variables. So in this case, R to the second power. So that means, according to lecture, a solution set of a homogeneous SLE is always a linear subspace. And of course, U1 is such a solution set, so obviously U1 is a linear subspace. So that's probably the shortest proof if you just use that general result here. And of course, that's totally fine for the exam. Okay, let's move on to part B. So in part B, we have a set U2. It's defined as x1, x2. Sorry, in R2 again. Where this time x1 times x2 is 0. So this defines a set U2, and the question is, again, is this a linear subspace of R2? And again, we start with checking whether the set is non-empty by simply checking whether it contains the 0 vector. So the first question is the 0 vector contained? And the defining property this time is the product of the two coordinates of our vector must be 0. And of course, if you check that for a 0 vector, 0 times 0 is 0. So that's obviously true. And that means the 0 vector is indeed contained in U2, and that means U2 is not empty. Okay, so the first property holds. U2 is not empty, so we can continue with the second property. Another question is the sum of any two vectors contained in U2? And if you think about this definition here a little, what that says is the product of x1 and x2 must be 0. x1 and x2 are real numbers. So what that means is that either x1 or x2 must be 0. So U2 contains all the vectors where exactly, or at least one of those two coordinates is 0. Of course, both can also be 0, like we just seen. So U2 contains all vectors where at least one coordinate is 0. And in particular, that means it contains the vectors 1, 0, 2, sorry, and it also contains the vector 0, 1. So those two are contained in U2. What about their sum? If we add those two, then the result is the vector 1, 1. But 1 times 1 is 1 and not 0. Oops, sorry. So this here, that's the vector where no coordinate is 0, and that is not contained in U2. And that means we have found a contradiction. We have found two vectors that are in U2, but their sum is not. So U2 cannot be a linear subspace. So that's an example of a counterexample. And in that case, it is totally sufficient to exhibit just two vectors that are in U2 and their sum is not. So it cannot hold for all pairs of vectors anymore. We've just seen one where it doesn't work. And that means U2 cannot be a linear subspace. Of course, the challenge here is to come up with a good example. In the end, please try to really write down one specific example. Sometimes people try to argue why this might not be the case or why there might be examples where this will work, and just fall short of writing down an actual example. And that is not bulletproof, because if you argue there might be cases where this may not hold, but still you cannot be sure. If you want to be sure, you have to show proof for that. And proof will usually be show actual numbers and then verify that these are actually proof of what you're claiming. Okay, so this works here. And of course, we don't have to check property 3 anymore, as property 2 is already violated. It doesn't make sense to do more work than necessary. It cannot be linear subspace anymore, whatever property 3 does. Okay, so that's part B of that problem. Any questions on that one?
Yeah, so like there is a question that it says like, when is it possible to say properties are inherited?
Sorry, I didn't get the last part.
Yeah, sorry, it says, when is it possible to say properties are inherited?
Oh, when is it possible to say properties are inherited? So in these two cases here, all elements of U1 and U2 are also elements of the larger space R2. And we know that R2 is a vector space. So that means all the properties of a vector space will certainly also hold for U1 and U2, right? So for example, associativity will work, the distributive laws will work, and all that. All the properties that we need for a vector space will work in U1 and U2 naturally. The only problem is that, of course, as a vector space, the addition of any two vectors will have to be in that same vector space. Otherwise, the addition is not well defined, right? You can't take two vectors and then land somewhere outside if you add them. And same thing for the multiplication with a scalar. The multiplication of a vector with any scalar must be in that vector space. Otherwise, the multiplication is not well defined. And that's the point we're proving here. So we're proving that U1 or U2 are closed or not closed with respect to these two operations. And if they are, then all the other properties of a vector space are inherited, because obviously the roots are the same on any subspace of a larger space, because they need to hold for all vectors of that larger space. So of course they hold in subspaces as well, just part of the larger space. I hope that was a question.
Yeah, Well, I would ask maybe the participants whenever there is like they got a result that to give a sign so that we know that we answered the questions. Like maybe you could scroll up a little bit. I think there were some students they couldn't really copy the homogeneous case. So yeah.
This part here, the alternative, yeah.
Then there was a question that it says, what's the difference between a subset and a subspace?
So a subset is just any subset, any collection of elements that are in the largest space. Take whatever you want. It doesn't have to have any kind of structure. You could just take a vector here and a vector here and another vector here. That's a subset of 3 elements. A subspace is a special subset. It's one that is closed with respect to addition and multiplication. So if you take these 2 vectors, for example, you also have to take their sum. If you take these 2 and their sum, you have to take this one and the sum, and this one and the sum, and of course the sum of 2 of these. And you have to take all scaled versions of all these vectors. And then you get a subspace, sorry. So subspace is more special. It's a subset that has vector space structure, so to say, that has this closeness property.
Then there is another question. I'm not sure whether like I understood properly, but it says, is it possible to do this step while the vectors remain as column vectors?
So in this case, what form the vectors have is really not relevant. Of course, we defined them as column vectors. So usually R2 consists of column vectors just by convention for us. You could do the same thing for row vectors, of course. And actually, you can do the same thing for vector spaces that are defined more abstractly, where they may not even be row or column vectors. Vector spaces could be very different beasts. For example, we briefly discussed in the lecture the example of the vector space of polynomials of a certain degree or up to a certain degree. And of course, there's no rows or columns there, but still these methods will work. It's just a little more abstract.
There is another question. It says, can you also prove the second case for question B like we did it for question A?
The second case, for, of course, I can quickly have a look at that. So let's have a look at case 3 and just let me note again that this is not necessary anymore. And it doesn't really matter what the outcome is. It's still not a linear subspace, whether 3 holds or not. But of course, we can have a look at that. So if we do that, we'd say, well, let X be contained in U2. Then that means X1 times X2 is 0. And let lambda be a real number. And then we have a look at lambda times X, which is lambda X1 times lambda X2, sorry, like this. And we need to check whether this product here is 0 or not. And if we do this, well, the first column is just lambda X1, the second column is lambda X2. So what we get here is lambda squared X1, X2. And we know that X1, X2 is equal to 0. Because X is in U2, and that was a defining property of U2, remember here? So obviously this is equal to 0. So that third property holds. But of course, still, U2 is not a linear subspace. Both properties have to hold in order for that to be true.
And then there are like some questions related, like whether you can prove it instead of like showing a contradiction or like finding a counterexample. There is some kind of like a confusion there because like, I think what I understand is like they are trying to do it the same way we did it for U1 instead of like trying to find a counterexample. Well, they could try, but it's not going to work, right? I'm not sure.
Yeah, right. It's not going to work usually. Yes. Yeah. So if you want to prove that something is not a linear subspace, then by all means, please try to find a counterexample. Of course, if you're not sure, what I would do is I would try to prove that it's closed with respect to addition and with respect to scalar multiplication. And on the way of doing that proof, I will at some point run into a hurdle that I cannot surpass anymore. And if that happens, I think about whether I could find an example where this actually is a hurdle that I cannot pass. So if I try this and find I'm stuck at some point, then usually I'm trying to find numbers that show me that this point actually will not work. And that will give me my counterexample. So to prove that something is not a linear subspace, please try finding a counterexample. To prove that something is a linear subspace, you have to prove these properties in general. So please do not just write down they hold for certain numbers. That is not sufficient.
Okay, then there is one student who asked why did he calculate 1, 0 plus 0, 1?
You probably refer to this one here. Yeah. So what I did there is I found a counterexample. And I came up with two vectors that were contained in that space U2, these two here, because they have 1, 0 coordinate each. And then I prove that their sum is not contained in U2, and their sum is 1, 1. And 1, 1 does not have the property that first coordinate times second coordinate is 0, so that's not contained in U2. So that is the counterexample I came up with. And of course, you have to show that your counterexample actually is a counterexample so that it really works. That's what I'm doing here. I'm showing that this really is a counterexample. The sum is not contained in U2 anymore.
Then I think there is like an interesting question saying, can I prove that any linear subspace is not empty set, is not the empty set by choosing any vector, or do I need the 0 vector?
Okay, so to show that a subspace or a set is not empty, you can just choose any vector that's contained in the set. Choose anything you like. Show that it actually is contained usually by verifying that it fulfills the defining properties. And then, of course, you have shown that it's not empty. The reason why I use a 0 vector is twofold. The first is, of course, usually verifying these properties is easy for the 0 vector. 0 something is usually the easiest you can have. And the second, more important reason for me doing this with a 0 vector is if the 0 vector is not contained, then I have my counterexample right away. Every linear subspace needs to contain the 0 vector. So if I have a set that contains other points, but not the 0 vector, then by showing that it does not contain the 0 vector, I'm already done. I already know it can't be a linear subspace, regardless of the rest. If I prove it contains some other point, then I will still have to look at the other properties. I have not excluded that 0 might be contained. And that's the reason why I'm usually looking at 0, but any other point will work too for that property.
Okay, there are some students that would like to see like how like the summation of the vectors doesn't work in U2. I think they are asking whether it could be possible to do it as the same case as in U1. And then like we did it with a counterexample in the solutions, and they would like to know whether it could be possible to do it just like taking a general vector. This is what I understand at least.
So you want to try the proof. Please don't do that. I'm not going to write that down. Do not encourage you to try that. So actually, if you want to show that a property does not hold, please provide a counterexample. Please write down actual numbers. Otherwise, there's always a possibility that your corrector is going to say, well, that's not conclusive. You have shown there might not be, the property might not hold. You have shown there might be a counterexample, but, well, you didn't show it, so maybe not. And that's the reason why you should always provide a counterexample if there is one. Just write down actual numbers. Don't bother with any general arguments. Of course, you can try that way to maybe get an idea of how a counterexample could look like. But in the end, just write down the counterexample and prove that it actually is a counterexample, and you're done. don't bother with any general reasoning. It will usually fail. At least it will cost you some points. So please don't do that. Okay, I suggest we move on to 3.2 if there's not any important questions anymore.
Yeah, let's continue.
Yeah, maybe we'll continue. So if there's any more you'd like to know about 3.1, just write to chat. We can always try to answer the questions later or maybe afterwards in chat. So let's move on to 3.2. So here we have a vector space that is given as the span of 4 vectors. Those 4 vectors are 1, 0, minus 2, 2, 1, 1, 4, 1, minus 3, and 0, 1, 5. And those are called V1, V2, V3, and V4. And now here's a couple of questions on that vector and on the vector space. So let's have a look at those. Just a second. First question, is a given set linearly independent? So let's have a look at that one. Is the set V1, V2, V3, the first 3 vectors, is that linearly independent? Now, what does linearly independent mean? Basically, the idea is that all vectors in this set are necessary to actually generate the span of that set. You cannot remove a vector and still get the same span. Formally, the definition was this. If you have a look at the linear combination of these 2 vectors using some lambdas, and if you try to find the linear combination that yields the 0 vector, so in this case, that would be 0, 0, 0, then of course there always is such a linear combination. One possible solution is always to set these lambdas to 0. 0 times anything will be 0, and if you sum up 3 zeros, then of course you'll end up with 0. So that is always a solution. The question is there more than just this one solution? So is there a solution for lambda 1, lambda 2, lambda 3 that is different from that one? And if there is, then we call these vectors linearly dependent. If there isn't, we call them linearly independent. And if they are linearly dependent, so if there is such a solution, then of course there is at least one lambda that is not 0. And that means we could solve for that vector. So that vector is a linear combination of the other 2. And that means we don't really need that vector to generate the span of V1, V2, V3. We could just throw that one out. So in that sense, the vector would be redundant. You should pay attention to not claiming that linear dependence would mean any vector could be expressed as a linear combination of the others. That's not true. Linearly dependent means there is at least one vector in that set that is a linear combination of all the others. That does not have to be true for every vector. There is one, but there also might be vectors where this doesn't work. So make sure to get that differentiation right. Now let's see how can we find out whether this set is linearly independent or not. One method, of course, would be to just use that very definition here. So let's try that first. So we want to find lambdas. So lambda 1, lambda 2, lambda 3, where lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 is equal to the all zeros vector. And we know v1, v2, v3, we have numbers for those. So we can just use those numbers. That is lambda 1 times 1, 0, minus 2 plus lambda 2 times 2, 1, 1 plus lambda 3 times 4, 1, minus 3. And if you look at that closely, then you will hopefully realize that is a system of linear equations. You can just take that row by row. So here we have that first row here. And that first row is simply lambda 1 plus 2 lambda 2 plus 4 lambda 3 is equal to 0. The second row, this one here, that doesn't have a lambda 1, there's a 0 here. So we have lambda 2 plus lambda 3 is equal to 0. And the third one is minus 2 lambda 1 plus lambda 2 minus 3 lambda 3 is equal to 0. So that's a system of linear equations in variables lambda 1, lambda 2, lambda 3. And basically we want to know whether it has more than one solution. 0, 0, 0 is obviously a solution. It's a homogeneous system after all. But we want to know if there is more than one solution to this system. And well, we can just find that out by solving it, right? So we solve the SLE. And to do that, we're putting it in a Tableau. So we have 1, 2, 4. We have 0, 1, 1. We have minus 2, 1, minus 3. So we're just using that Tableau. The right-hand side is 0. I'm just going to leave that off. And then to solve it, well, what we could do is we take this here as our first pivot element. We're good here already. We just need to obtain zeros down there. And to do that, we just add the first row 2 times to the last one. And we get first row and second row. We can just copy those two. And the last row becomes minus 2 plus 2, that's 0. 1 plus 2 times 2, that's 1 plus 4, that's 5. And minus 3 plus 2 times 4, that's minus 3 plus 8, that's 5 again. And now for the next step, we take this pivot element here, and we subtract it 5 times from the third row. And we get 1, 2, 4, 0, 1, 1, and 0, 0, 0. So we have 2 pivot elements, this and this one. And what that means is, well, we have 3 variables. We have 2 pivot elements, so the rank of the matrix is 2. And that means there's more than one solution. So the SLE has more than one solution. And that means 0, 0, 0 is not the only solution. And that by definition means that set V1, V2, V3 that we started with is linearly dependent. We don't even have to compute the solution. We just need to know whether there's just one, 0, 0, 0, or more than one. So that's all we do here. So any questions about this problem before we go on?
Yeah, so there is a question that it says, is there a difference between dimension of vector space and dimension of solution set of the system of linear equations?
Well, the solution set of the system of linear equations, a homogeneous system of linear equations, is a vector space. The dimension of that solution space is just the dimension of that very vector space. The only difference is if we have a non-homogeneous system, then the solution space would not be a vector space, it would be an affine space. You may have watched today's first or second video, second I think already, where we talk about affine spaces. So basically that's a vector space that is translated. And the dimension of an affine space is defined in basically the same way. It's just the dimension of that vector space if you translate it back. So again, the dimension of the solution set and the subspace coincide. That's the same thing.
Then there is a question that it says, can you prove independency by using the row echelon form?
You can prove independency by using the row echelon form. That is right. Yeah. Let me go into that. So this first method that I was just showing you, that basically use this definition here, this one, and then try to actually find or at least see how many lambdas there are that solve this system. There is a way that almost does the same thing, but it's slightly different. What we can also do is we could try to form successive linear combinations. Let's put it this way. So we have these three vectors. Let me start with those. We have the vectors 1, 0, -2, 2, 1, 1, and also 4, 1, -3. And basically the question that we're asking here is, can we come up with a linear combination that yields the 0 vector other than the trivial one? So what we could try is we could just try to find such a linear combination in a more or less systematic way. Of course, one way would be to just guess. Yeah, you can do that. If you want that a little more systematic, then we could try the following. We could try to add and subtract the vectors in a way such that the first coordinate could become 0. And then once we have the first coordinate, we do the second, and then we do the third. And hopefully we're successful at that at some point. So if we can do that, then we also have found a linear combination, at least implicitly, that will do what we want, and it's not the trivial all zeros combination. So basically what we're doing here is almost the same as Gaussian elimination. We're using these vectors, and then we're trying to set the first coordinate, or the first column in that case, to 0, then the second and the third. So you could also do that. You could just take these vectors, and just because I'm used to doing Gaussian elimination in rows, I'll now write them in rows. So I do it this way. Yeah, you see this here, the first vector is this one here, the second vector is this one here, and I need another color. The third vector is this one here. I just wrote them as rows because I want to operate on rows. You could also transpose this thing if you wanted to. It doesn't really matter. And now what I'm trying to do is I'm trying to use combinations of these to form a 0 vector. And the first thing I could do is I could use this one here, sorry, this one here as a pivot element. And I could try to combine the first row with the other two to get zeros in the first column. So if I'm doing that, then of course I have to subtract 2 times row 1 from the second and 4 times row 1 from the third. So I would get 1, 0, -2. I just copy the first row. The second becomes 0, 1, and we have 1 plus 4, that is 5, hopefully. And for the last row, I'm getting 4 minus 4, 1 minus 0, and -3 plus 4 times 2 minus 3 plus 8, that's 5 again. And so now I have 3 new vectors that still have the same span. I just took linear combination, so that doesn't change the span, right? So what I did here is basically the span of these original three vectors, these three here, is equal to the span of those vectors here. And again, I'm using the rows now as column vectors. I was just using rows before because I'm used to doing Gaussian elimination in rows. Basically what I do here is I'm just taking a linear combination. I combine this row minus 2 times the first row. So that's a linear combination of those first two vectors. And here I'm combining that one with that one. So again, a linear combination of two vectors. I replace those by linear combinations. So the span is the same. And the idea is to continue this process until I end up with a zero vector in the span. And of course, I don't need a zero vector. I can always do away with that. So if I get in a situation like that, then I know there is a vector that's irrelevant, and I know the original set has been linearly dependent. That's actually what happens in the next step. So let's do that. Let's do that as well. If I take this as pivot and just subtract the second row from the third one, then what I get is a zero row in the last row. So next step, this is the same span as this one here. Just keep the first two vectors, and the last one is now the all zeros vector. And of course, I don't need the all zeros vector for the span, so I could just do away with that. And that is the same span as just the first two vectors. Okay, so that means that last vector, that actually was a linear combination of the first two. So V3 is a linear combination of V1, V2. And that means that set that contains all three vectors, that is linearly independent. Linear dependent, of course. Okay, so I could also do this to find out whether that set is linearly independent or not. The downside of this method is I couldn't just write down the right linear combination now. It was obtained using several steps. And of course, I could kind of backtrack my steps and see what I did and then combine this and somehow obtain that linear combination. But if I actually wanted that, then the method of just solving this SLE here is probably much easier. That would give me the right lambdas right away. But if I don't want the linear combination, if I just want to know whether the vectors are independent or not, then this method here is totally fine. Yeah, you can just do that. And we will do that frequently. So I hope that answered the right question here, or at least provided some interesting insight. Any other questions?
Yeah, so I think these are kind of like easy to, quick to answer, like whether they could write it also in the Tableau form and try to solve with Gaussian elimination.
Yes, of course, you can also use Tableau form. I basically did that here.
Then there are some questions related, like how does the rank influence the solution, or how does it impact on the solution, the rank?
So if you have a look at this last matrix here, for example, when was that? This one here. You can see that has two pivot elements. So the rank of that is 2. And the matrix is a 3 by 3 matrix. So the number of solutions is basically determined by the number of columns or the number of variables and the rank. If those are equal, then there's a unique solution for the homogeneous case. If the rank is lower, then there's 3 variables, and that always means more than one unique solution. So that's the case here. Any more questions?
Yeah, there is another one. Can we just calculate the basis of V1, V2, and V3, and then see that we just get 2 vectors as the basis, so we could conclude that V3 is linearly dependent?
Yes, yeah, of course, you could also do that. You could just say, I'm going to compute a basis for the vector space that is spanned by v1, v2, v3. And if the basis contains only two vectors, then obviously 3 must be linearly dependent. That's also totally fine. And basically that's what I did here, by the way, right? So if you're looking at that approach here, I manipulated the vectors such that in the end, I found that I only needed these two to span the same space as this spanned by these 3 vectors. So what that means is basically this set here, these 2 vectors, that's the basis for the span of v1, v3, v1, v2, v3.
Okay, and maybe I read just one last one. It says, how do we know which one of the vectors is the linear combination if we use the first method?
So if you use the first method, I didn't solve that to the end, but what you could of course do is, once you're here, you could then write down the actual solution. And that will let you know which lambda combinations are allowed. And then if you find a lambda combination where, let's say, lambda 1 is not 0, then of course you can use that and solve for v1. So v1 is a linear combination of the other 2. If you find a lambda combination where lambda 2 is not 0, you can do the same for v2. Then v2 is a linear combination of the other 2. And in that case, if you actually try to do that, and it's probably a good exercise to try that at home, then you will find out that in this case, any of those 3 vectors can be expressed as a linear combination of the other 2. So in this case, it doesn't really matter. But there are cases where it does matter. So if you find out there's only lambda combinations in my solution set where lambda 2 is 0, then you can never solve for lambda 2. So v2 cannot be expressed as a linear combination of the others in such a case. Again, that doesn't happen here, but there are such cases. So you should pay attention to that one. And if you want to find out which vectors you can express as linear combinations of some of the others, then you just have to solve this here until the end and write down the actual solution set. So we did 3 to A, and actually that was the longest one, so the rest should be shorter. Part B, I wrote down the vectors that span that space V once again, and part B is the question, write V4 as a linear combination of V1 and V2. And to do that, what we need to do here is we need to find, sorry, just a second, we need to find lambda 1 and lambda 2 in the reals such that V4 is equal to lambda 1 V1 plus lambda 2 V2. And of course, we don't yet have a guarantee that this will actually work. So there might not be such lambdas, but we'll find that out when we try to find them. So basically, it's the same thing as before. We need to solve a system of linear equations. That looks like lambda 1 times V1. V1 is 1, 0, minus 2. Plus lambda 2 V2, that is 2, 1, 1. And the right-hand side is now V4, which is 0, 1, 5. Okay, once again, so we have to find lambda 1, lambda 2 with this property here. And again, that just amounts to solving a system of linear equations. I won't write out that system. I just go to Tableau form straight away. That means we have to solve this system here with the right-hand side of 0, 1, 5. And that shouldn't be much of a problem. Again, we'll add 2 times the first row to the last one. And we get 1, 2, 0. So the first row isn't changed. The second row is not changed either. And the last row becomes 0. And 1 plus 2 times 2, 1 plus 4 is 5. And 5 plus 0 is again 5 here on the right. And then we'll subtract 5 times the second row from the last one. And again, we copy the first row. Again, we copy the second row. And the last one becomes 0, 0, 0. So we get a solution. We have 2 pivot elements here. we have a 0 on the right for the 0 row, so that's not a problem either. And that means we can just solve that system here. We first solve for lambda 2. Lambda 2 is 1. That's simply this equation here. And then we solve for lambda 1. And the first equation here that says lambda 1 plus 2 lambda 2 is 0. So if you solve that for lambda 1, then we get lambda 1 is minus 2 lambda 2. We know lambda 2 already. So let's just substitute that here and we get minus 2. And that means the final result here is minus 2 times V1 plus V2 is V4. So V4 is indeed a linear combination of V1 and V2. And here are the coefficients, minus 2 and plus 1. Any questions so far?
No. No, there isn't.
Part C, let me just scroll down. Yeah, part C, determine a basis of V. So in part 3, we are finally going to determine that basis of V. With the work that we did already in A and B, that's actually going to be really easy. We have already established in part A, remember, that V1, V2, and V3 are spanned by these two vectors, and they are actually bases of the span of V1, V2, V3. V3 is linearly dependent of those, so that can be expressed as a linear combination of V1 and V2. And we just established the same fact for V4. So we know that V4 and V3 are linear combinations of V1 and V2. And in A, we've also established that the set V1, V2 is actually linearly independent. And well, what does it mean? That means we have a linearly independent set, V1, V2, that spans the whole space. So the span of V1, V2 is the same as the span of V1, V2, V3, and V4. And that means the basis that we are looking for, that is simply given by V1 and V2. A linearly independent set that still spans the whole space. And from the facts that we computed in A and B already, we know how that set looks like. Questions to that one?
Yeah, so there isn't a zero that it says, sorry, a question that it says, what would happen if the last row wouldn't be just zeros?
If the last row wouldn't be zeros, I'm guessing you're referring to this one here?
Yeah.
Then if you're already done, so if that is actually Echelon Form and the last row is not all zeros, then that means you will not be able to find a solution, I guess, or at least not a solution for all the systems. So if that happens, you still have these two pivot elements, and you have an equation here that might contradict those. And it will contradict those. The left-hand side will always be zeros because we make it that way. The right-hand side might not be zero, so you get a contradiction in the form 0 is not 0. 0 is 5 or something like that. If that happens, you know that there is no solution to the system of linear equations. And that means you cannot find lambda 1, lambda 2 with that property here. So V4 is not a linear combination of V1, V2. So that would give you that information.
Okay, another question is when and how do we decide if we write the vectors in columns or in rows in the Tableau form? I did not grasp the difference. This is what the question is.
Okay, so that depends on what we're actually trying to solve. So in this example here, we are trying to solve this system. And that means we have basically 3 rows. This row here, this row here, and this row here. And if we write these rows in the Tableau, then you end up with these vectors here in the columns, like this. So basically, whenever you're trying to solve a system of linear equations that involves vectors, then those will end up as columns of your Tableau. We did something very different, at least formally different here, where we wrote the vectors as rows of our matrix. So what we did here is we took those vectors and we tried to find linear combinations of those that yield the 0 vector at some point. And to do that, well, taking a linear combination basically means I'm adding and subtracting multiples of one vector and some other vector. And I can repeat this procedure again and again to get more complex linear combinations that involve more than one vector. And that's what I'm trying to do here. So basically, I'm putting these as lines in a matrix, and then I'm taking linear combinations of these lines. Here I'm combining the second green line with the first orange line. I'm taking 1 time this green line and -2 times the first one, the orange one, and I'll end up with this one. And here I'm forming a different linear combination. I end up with this one. And then I'm taking the new one, this one here, and combine it with this new one to obtain the 0 vector. That was the basic idea here. Basically, I am using steps that are the same as doing Gaussian elimination. So forming these linear combinations of pairs of vectors is basically the same as doing a Gaussian elimination step. And that's the only reason why I'm writing these as lines in a matrix. I'm used to doing Gaussian elimination. So I'd like to do just that as I'm used to. And that means I'm writing those as a line so that I can do Gaussian elimination as I usually do using rows in a matrix. And at the end, I obtain my 0 vector as a row. I could also do this as columns, or I could do this without the Tableau. It doesn't really matter. It's just because I want to use this method that I'm used to and that I've practiced over and over again so that I know how to do it and I won't make any mistakes that way. And that's the reason why I'm using that. Okay, hopefully that answers this question.
How could you find the basis without having the information from A and B?
Yeah, of course, we can find the basis without having that information. Basically, we kind of reproduce the computations we did in A and B. So let me see if I can demonstrate that. So here's the vectors once again. We want a basis of V that is spanned by V1, V2, V3, and V4. And what we could do is we could again take linear combinations of those vectors with the aim to produce as many 0 vectors as we can, and those will be the vectors that we don't need. So we'll do the same trick as before. We'll write the vectors as lines of a matrix like this. So now we have all 4. And then we try to do successive linear combinations and try to produce as many 0 vectors as we can, and then just strike those, leave those out. So what would happen? Let's do that. So we subtract 2 times the first line here, 4 times the first line here. There's a 0 here already, so we're good. That means we're getting, the first row is just being copied, 1, 0, minus 2. The second would become 0, 1, 5. The third becomes 0, 1, plus 8, that's a 5 again. And the last one is already 0, 1, 5. And now you can see I just take the second row and I subtract it from the third and also from the fourth. And I get 1, 0, -2, 0, 1, 5, and then 2 0 rows. So that means I can now just take these two vectors that remain, and I know these will span my vector space V. And they are obviously linearly independent, because if you look at their pivot element here and here, if you want to produce the 0 vector using just those two, you'd obviously have to use 0 times this first one, because otherwise you would have some multiple of 1 in the first coordinate. It can't be made up here. Oops, sorry. Can't be made up here with a 0. And then, of course, you'd also have to use 0 times the second one, because if you have 0 times the first one and then add something that is non-zero, you'll not end up with a 0 vector. So obviously those are linearly independent. And that means, that means a basis of V is also given by 1, 0, -2, and 0, 1, 5. So again, we end up with a basis doing basically the same method we used before. That hopefully answers this question. Any others?
Yeah, well, there are quite a lot. Wait a second. Why is the span of V1, V2 equal to the span of V1, V2, V3, V4? I'm not sure whether I understand this question properly. Maybe rephrase it.
Can we try to rephrase that and we take another question first?
Yeah, how do we generally show that the span of B is equal to V as it is requirement for the basis?
Sorry, the span of what is equal to?
Like a span of B, like B of Bavaria, equal to V of Vancouver.
Okay, so the question is, how do I show that a given set really spans a vector space? So something like a span of B is some given set is really V.
Yeah.
So B is some given vector space. I cannot really answer that in general. That all depends on how V is actually given. In that case, it's easy because V is defined as the span of a set of vectors. So obviously those vectors will span V by definition. That might be different, and we can actually have a look at, we'll see that in 3.1 if we do the basis for that one. I can do this in just a minute, but maybe there's other questions first.
Is another basis consisting of V1 and V4?
Yes, you could also take V1 and V4. Yes, I'm not going to prove that now, but yeah, this basis that I've shown here is by no means unique. We've already seen two different bases. V1, V2 was the first one. This here is the second one. There's lots of other bases that you could come up with.
Can a basis be expressed as the most reduced vector span?
So you could say something like a basis is the smallest subset of the vectors in that span that still have the same span. In that sense, yes, it's the most reduced vector set that still create the same space. The minimum generator, if you want.
Would it also be possible to take a look on the vectors, and if one of them is a multiple of another one, we know that one of them can be left out?
Yes, so if one vector is a multiple of another one, then obviously it's a linear combination of just that one vector, so you can leave out any one of those two. Usually it's not that easy. So in this case, for example, if you look at those four vectors, no one is a multiple of the other. You need at least two vectors to combine one of the others in this case. But if it's that easy, then of course, yes, you could just leave out multiples.
So then there is a question, there is somebody very confused about linearly dependent and independent, because like in part A, we said that V1, V2, V3 is linearly dependent because V3 is linearly dependent of V1 and V2, but V1 and V2, they are linearly independent between each other. I'm not sure whether this is what it is. It is a confusion. It's like why in A was linearly dependent and now V1 and V2 are independent, right?
Yeah, because we reduced the set. So in A, we had the set V1 V2, V3, that was linearly dependent. And linear dependence and independence is always a property of a set of vectors, not of single vectors. You're always talking about a set here. So this set here is linearly dependent, and that means there is at least one vector in that set that can be expressed as a linear combination of the others. And obviously, if we use that set, then we might lose that property. In this example, we've seen that V3 is a linear combination of V1 and V2. So we can just drop V3 and only keep V1 and V2, we get the same span. And now that new smaller set, of course, that could still be linearly dependent if V1 and V2 were multiples of each other. Or in this case, they're not. So this set is linearly independent now. So basically, you can take any set, and if it's linearly dependent, you can just delete vectors from that. And at some point, you will get a set that is linearly independent. So in that sense, you can also say a basis is a smallest possible linearly independent. No, that's wrong. That's one possible, or largest possible linearly independent set. Sorry, a linearly independent set that still generates the full space, and that's the case here for V1, V2. Still generates the same space, but now we've reduced it as much as possible without losing anything. If we delete one more vector, then we will lose something. Then the span will be reduced. I hope that clarifies why we've moved to a linearly independent set.
Yeah, then there is another one that it says, when do you stop trying to resolve rows and vectors?
Sorry, when are you trying to resolve?
When do you stop retrying? Yeah, like when do you stop trying to? Yeah, maybe again, like rephrase this question because it's not really clear to me neither.
Yeah, please do. I don't really get what you mean here. Try
Okay,
to rephrase that, please.
Let's take one last one. When do we know if we have to write the vectors which we transform into a matrix, row or column wise? Well, this was already answered.
Yeah, we talked about this already.
If V1 and V2 is linearly independent, it is automatically a basis of V.
So if V1 and V2 is linearly independent and spans V, then, so if the span of those two is V, then it is a basis of V, yes. So you'd have to have those two things. Linearly independent alone is not sufficient, because if you just take V1, for example, just this set, that is also linearly independent. But the span is not V, so that doesn't span V. That means this is, of course, not a basis for V. It's not sufficient. Yeah, but this here is. That has both properties. It spans V and it's linearly independent. So our basis always needs to do both. Okay, I said let's move on.
Yeah.
And we can always try and answer more questions at the end. D actually is easy. D asks for the dimension of the vector space V. The dimension is simply the number of vectors in any basis. We had a basis here that contained V1 and V2. So there's two elements in that basis, and that means the dimension is 2. So I'm guessing I'll do E as well before we take any new questions. Find a vector in R3 that is not contained in V. So the reasoning here is V is a subspace of R3. The dimension is 2. The dimension of R3, on the other hand, is 3. So there must be vectors that are contained in R3, but not in V. Otherwise, the dimensions would agree. Okay, V is strictly smaller than R3. And the task here is to find such a vector, any vector that you like. So basically, we can just take what we know about V so far. And we know that V is the span of two vectors, V1 and V2. So that means it's the set of all linear combinations of those two vectors. Let me copy those once again. So here's our vectors. So remember, V1 is 1, 0, minus 2. V2 is 2, 1, 1. So this here is the set of all linear combinations of those two vectors. Now we need to find a vector that cannot be expressed as a linear combination of those two. How do we do that? What we want to have is, we want to find some, let's call it B in R3, such that the system lambda 1 times 1, 0, minus 2 plus lambda 2 times 2, 1, 1 is equal to B, such that this does not have a solution. How do we go about that? Well, it's actually not that hard because we know a lot of those already. Remember, if you write this down in the form of a tableau like this, it looks like this, and then we have B1, B2, B3. We know already that the rank of the left-hand side is 2. So we can just try to solve that and then select the B's in a way such that we can see there is no solution. Now, to make things a little easier, it's of course sufficient to prescribe one of those coordinates of B. We can just select the other ones. As you can see here already, the first two rows here, together with those right-hand sides, that's a system of two linear equations in two variables. And if you just look at those, let's mark those actually. If you just look at that subset here of the equations, and you can see this is already in echelon form. Here. Just ignore the third row for now. We could solve this subsystem already. So we could solve that for lambda 2 and lambda 1, and that means lambda 2 and lambda 1 will be determined by that subsystem already. So let's just come up with B1s and B2s, anything, to determine lambda 1 and lambda 2. And then we select a B3 that contradicts that. So for example, set B1, let's see, let's say we want lambda 2 equal to 1 and lambda 1 also equal to 1. Then that means we have to set B2 equal to 1 and B1 equal to 3, right? 1 plus 2. So if we do this, we get a 3 here, a 1 here, and we still keep the B3. We need to adapt that B3 such that there is no solution. So now let's try and solve this system. If we do that, we just add 2 times the first row to the last one. And that yields, let's see, 0, 5, and 6 plus B3. And then we subtract 5 times the second row from the last one. And we get 1, 2, 3, 0, 1, 1, and 0, 0. And here we have 6 plus B3 minus 5. So that's 1 plus B3. So now we can see we'll only get a solution if this here is 0. So we have no solution if 1 plus B3 is not 0. So any B3 with that property will do. And we just select an arbitrary one. For example, select, let's say B3 equals 0. And then we get the vector B. We already selected B1 and B2 before, 3 and 1. And now we selected B3. So we have a vector 3, 1, 0 that is not contained in V. So we just computed a vector that does the job. And of course, there's a whole lot of other solutions that will also do the job. So, any questions?
No, there isn't any, so we can continue.
Wonderful. Okay, finally, part F. In part F, the task is to find a basis of R3 that contains V1 and V2. And again, we did a lot of work already, so we basically set to answer this question easily. We know that V1 and V2 span the space V. And we also know a vector that cannot be expressed as a linear combination of V1, V2. And that vector is 3, 1, 0. So that means the set V1, V2, and that new vector 3, 1, 0, that will be linearly independent. And it will span R3. Yeah, we have 3 vectors now. So the space they span is 3-dimensional. Any 3-dimensional subspace of R3 needs to be R3 necessarily. It can't be smaller than that. So that is R3. So this set here, that is a basis of R3. And it contains V1 and V2. So that completes exercise 3.2. Any questions remaining?
No, but maybe somebody asked, maybe you could go a little bit like scroll up so that they couldn't finish copying it.
I put this lecture notes online, by the way, in just a minute after I finish this one. So if you didn't finish writing this down, you can always look it up on Moodle in about half an hour or so.
Could we use the X product to find, so the product to find 1?
You meaning to try the vector product? Yeah, in R3, yes, you could do that. We will probably not talk about the vector product in this lecture because it just works in R3. It does not work in any higher dimensional spaces. So it's pretty much useless if we're talking about general vector spaces. And I do know it's often used as we're talking about 3-dimensional spaces in many applications, but you can live fine without that. And of course, if you want to use it for this particular problem here, you could do that. But I guess there would be even more work than my solution.
Maybe computing now the basis of 3.1a.
Yeah, I'll do that now. That's a good point. So let's try to do that now. So we want a basis for U1 from C 3.1a. So remember, U1 was defined as all x1, x2 with x1 plus 2x2 equals 0. So I've said it before, U1 is a solution set of a system of linear equations, homogeneous system of linear equations, which means we know it's a vector space, and which also makes it easy to come up with a basis. And to do that, we just determine the solution space explicitly first. So in this case, we only have one equation, so that already has echelon form necessarily. So we have the SLE. If we want to write that in Tableau form, that would be 1, 2, 0. Here's our pivot element. That means the variable x2, there's no pivot in the column that corresponds to x2, though that is a free variable. And this pivot here corresponds to x1. So if you want to solve that, then x2 is free. And we solve for x1. x1 is, let's see, minus 2x2. So what we get is the solution space, which is U1, is the space minus 2x2, x2, with x2 in R. And that could also be expressed as x2 times minus 2, 1 with x2 in R. And that is, well, that's just a set of all linear combinations of this one vector of minus 2 and 1. So we could write this as the span of minus 2 and 1. So we have a vector that spans U1, and it's only one non-zero vector, so of course it's linearly independent. So this set here, that is a basis of U1. So U1 is one-dimensional. And that's how you could compute the basis for this vector space U1 here. Any other questions we should answer?
Okay. Sorry, I couldn't unmute myself. Yeah, maybe could you explain again quickly the reasoning in part E?
The reason in part E, what was part E again? Find a vector that's not contained. Yeah. Okay, so what I did here is I want to find a right-hand side B here such that this system of linear equations cannot be solved. And if I write that in Tableau form, it looks like this. And you can see, well, I have two variables. I have three equations. So if I'm looking at the first two equations, I can see that the rank of this submatrix is 2 already. So that means we have a pivot here and a pivot here. And we'll have those pivots even if we compute Echelon Form. So that means I could solve the whole system with only these two equations already. Right? The third one won't do anything for the solution. So that means if I prescribe B1 and B2, any B1 and B2, then I can already determine lambda 1 and lambda 2 uniquely. And on the other hand, there is really always a solution for any B1, B2. So just select anything you like. And I just selected 3 and 1 more or less randomly. You could use any other numbers here, anything you want. Then I put that here in my system. And I know this is sufficient to solve for lambda 1 and lambda 2. So if I'm now solving my system, I'm bound to get a 0 row in the third row. The first ones will already do. So there needs to be a 0 row in the last row. So I'm solving. I'm getting that 0 row here. And I still have my general right-hand side, my B3, here and here again. And now I can have a look at that whole row. And that gives me an easy condition to see whether the system has a solution or not. The left-hand side is 0. So if there is a solution, the right-hand side needs to be 0 too. So if I don't want the system to have a solution, I need to select B3 such that this is not 0. And then I know there is no solution to that system. And that's exactly what I'm doing. I can select any B3 such that this is not 0. So -1 wouldn't be a good choice because then this orange expression is 0. Anything else will do. So for example, I just choose 0. I could have chosen 42 or pi squared or whatever you want as long as it's not -1. Yeah, and same thing here. Those 3 and 1, basically that's arbitrary. I could have chosen anything in that place here. The result would have been different, but still I would have gotten a vector that's not contained in V, but in R3. So that's what I did here in part E. Any other questions on 3.2?
How did we get that V1, V2 is the span of 3.2?
How do we get that? That basically was solved here in, I think it was C. No. Yes, C. I'm missing a C somewhere. So the idea was In A, we proved that V1, V2, V3 is linearly dependent. Then later in B, we proved that V1, V2, V4 is linearly dependent. So V3 and V4, we proved that those vectors are linear combinations of V1 and V2. So V1 and V2 are sufficient to span V. The only remaining question is, are they also linearly independent? And we've seen that as well before. V1 and V2 are linearly independent. So we know those are a set, a subset that still span the whole space V and are linearly independent. So that's a basis. That's how we got this.
There is a quick question. Could you explain F again, please? And maybe after this question, we kind of like move on.
Yeah, so I'll take that question. Then we move on to 3.3. That's actually not a long one, 3.3. Okay, so F is the question, find a basis that contains V1 and V3, V1 and V2 and spans R3. So we have V1 and V2 already. We know that spans a subset V of R3. And we want to add a vector to that such that the span is the complete R3. To do that, we need another vector such that the new set, this one here, is linearly independent. And if that is the case, then of course the span will be three-dimensional. And a three-dimensional subset of a three-dimensional space needs to be the space itself, can't be smaller. Right? So we need to add a vector such that this new set is linearly independent. And we have, in part E, we have computed such a vector. We know that this one here cannot be expressed as a linear combination of V1 and V2. That's how we made that vector. So if we just add that to the set, then that new set will be linearly independent. And that's why it spans R3 and is linearly independent. So we have a basis of R3. And it contains those first two vectors. So I hope that answers the question. So let's go on to C3.3. That shouldn't actually be that much of a challenge. So there's a system of linear equations with a parameter, and the task is to determine the dimensions of the solution set dependent on the parameter. So as always, if we have a system of linear equations, we usually do Gaussian elimination. So let me write down the Tableau form of that system right away. So that is 1, 2, and there's an alpha here before x1. Then we have 0, 1 minus alpha, 1 minus alpha. And here we have alpha, 3 minus alpha, and 1. And the right-hand side is 0, so I'm just going to omit that. So if you want to solve that, then we start with taking this here. This 1 is our first pivot element. And we just subtract 2 times the first row from the second to get rid of that 2. And we subtract alpha times the first row from the third to get rid of the alpha. And notice that I don't have to make a case distinction here. If alpha is 0, that's not a problem. Then I'm just subtracting 0 times something, so I'm not doing anything. And if alpha is 0, that's fine because there is a 0 already. Yeah, so no need to make a case distinction here. So what do we get? We get 1, 0, alpha. Then we'll have 2 minus 2 is 0. 1 minus alpha minus 0 is 1 minus alpha. And we have 3 minus alpha minus 2 alpha. So that's 3 minus 3 alpha. And in the last row, we get, let's see, alpha minus alpha is 0. 1 minus alpha minus 0. Nothing happens here. And here we get 1 minus alpha times alpha. So 1 minus alpha squared. Okay. next step we're going to do is we're going to subtract the second row from the third one. We're going to use this here as our pivot element. Again, notice we don't have to make a case distinction. We're not multiplying or dividing by alpha. If that expression happens to be 0, then we're all good, right? Then we have zeros anyway. So what do we get? We have 1, 0, alpha once again. We just copy the second row. That is 3 minus 3 alpha. And the last row, that becomes 0. Here we get 0. Until we have 1 minus alpha squared minus 3. So that's a minus 2 plus 3 alpha. And we keep the 1 minus alpha squared. Yes, that should be the right one. Okay. So now we have echelon form, right? These could be pivot elements. They could also be 0, then they will not be pivot elements, but at most these 3 pivot elements here. And now basically we'll have to find out whether they are pivot elements. If they are all pivot elements, then the rank of the matrix is 3, and that means there is a unique solution. If one of them is not a pivot element, then the rank is less than 3, and we'll have more than one solution. So let's see about that one. Basically, we have this expression here, 1 minus alpha. The roots of that are easily seen. That's just 1. Now we have that expression here. That's a little harder to see, but you all know how to compute roots of quadratic expressions. At least I hope you do. So we can also compute the roots of this one. So the roots of 1 minus alpha, or the root of 1 minus alpha, is alpha equals 1. The roots of minus alpha squared plus 3 alpha minus 2, we just reordered that. If you compute those, you will find the results are 1 and 2. So again, the 1 and another one, which is 2. Okay, that means our echelon form can also be written in this way. If I want to see the roots right away. Sorry. 3 minus 3 alpha. And the last one, so this is obviously the product of alpha minus 2 and alpha minus 1, and a minus in front of that. Okay, I know that because I know the roots. So the cases I have to look at are alpha equals 2, alpha equals 1, and alpha is anything else. So let's have a look at those. First case, alpha is in the reals, but not 1 or 2. If that's the case, then 1 minus alpha is not 0. And this expression is also not 0. So we have 3 pivots. The rank is 3. So that means 3 pivot elements. Rank is 3 of that matrix. And that means there is a unique solution. And as the system is a homogeneous system, that unique solution is, of course, the 0 vector. That's always a solution of a homogeneous system. So if that is unique, there is no other solution. And that means the dimension of the solution set, I'll call that solution set S, the dimension is 0. 1 point, that's a 0-dimensional space. So let's look at the case alpha equals 1. What I get then, if I take a look at this matrix here, let's copy that. What I get then is I'm getting a 0 right here, and I'm also getting a 0 here. And alpha equals 1 also means 3 minus 3 alpha will also be 0. So 0 is all here. We have 2 0 rows. We only have this one pivot element left here. One pivot. That means the rank is now 1. So we have 2 free variables. The dimension of the solution space will be 2. And finally, for the case alpha equals 2, let's again copy that matrix here. So if alpha equals 2, then this here is again 0. But this is not. And that means we get 1 0 row, but we have a pivot element here and we have a pivot element here. So that means 2 pivots. The rank is 2. And that in turn means the dimension of the solution space is going to be 1. It's going to be 1 free variable. Okay, so that's the 3 cases that I have here. And basically, I'm getting almost all possible dimensions here. So that completes 3-3. Any questions about that one?
Yeah, there is a question that it says, I haven't learned how you take the root of alpha.
You haven't learned how to compute the root of this quadratic expression here, you mean? I'm guessing.
What I understand, yeah.
Yeah, so you should brush up on that. There's a straightforward formula for that. I can tell you the formula, but probably won't help that a lot. So if I have this minus alpha squared plus 3 alpha minus 2, then what I'm doing is I can find out alpha 1, 2 by using the formula that goes like this. Actually, I'll write that down in general first. Let me copy that so I have some more space. Sorry. Down here. So I want to solve this one. There's a general formula for quadratic expressions that look like this: ax squared plus bx plus c. And it goes like this. The 2 possible solutions can be obtained as minus b plus minus the square root of b squared minus 4 times a times c divided by 2a. So that's the general formula for quadratic expressions, and that's exactly what we're going to use here. So in this case, our b is plus 3, our a is minus 1, and our c is minus 2. So that's what we're going to use. And if we do that, we get minus b is then minus 3 plus minus the square root of b squared. That's a 9. Minus 4 times minus 1 times minus 2, that is a minus 8, divided by minus, well, by 2a, so 2 times minus 1, that's minus 2. And if you compute that, you get minus 3 plus minus the square root of 1, that's just 1, over minus 2. So that should be 2 and 1. Okay, I hope that helps.
What is the dimension if I have 4 elements and 4 system of equation rows? What is the dimension if I have 4 elements? I guess like 4 elements
So if I have a 4x4 system, 4 variables and 4 rows, probably.
Is the dimension the cardinality of the basis?
So the dimension that we're looking here, so this problem asks for the dimension of the solution space. You always need a space, a vector space to define dimension. So you need to make sure what vector space we're talking about. And in this case, it's the solution space of the homogeneous system associated to that matrix. So if we have a 4x4 matrix, we definitely have all the possibilities here from 0 to 4. So the solution space could be 0, could just consist of that one point. It could be a 1-dimensional subspace, a 2-dimensional subspace, a 3-dimensional subspace, or it could be the whole of for everything. So it's all in the books.
I think there are like some questions related to why do we know the dimension from looking at the number of pivots and the variables? How do we know the dimension from knowing the number of pivots and the rank? There are like several questions in the same.
Okay, so basically what we do if we solve a system of linear equations is we're doing Echelon Form, and we determine the pivots, and then we know which columns do not have pivots. Well, those are going to be the columns that correspond to free variables. And as you've seen before, basically the solution space depends on those free variables. So every free variable kind of gives you 1 degree of freedom if you want. So let's just have a look at one of those solutions we had, like this one, for example. We had this system of linear equations here. There was 1 pivot, 1 column without a pivot. So we know that is a free variable here. And we could just solve everything depending on that free variable. So our solution looked like this, or written in a more elaborate way like this. So what we get here in that example is a solution space that is spanned by 1 vector. Now, in general, what we get is one of these vectors for every free variable, and those will automatically be linearly independent, because for the free variables, the vector that comes with that free variable, so to say, that always has 1 in that position, and a 0 for every other free variable. There's no others here, so we can't really see that. But let's say I'm just making up a solution space. So it may look something like, let's say, x2 times -2, 1, 0, plus x3 times -7, 0, 1. So if we have like 3 variables, 2 free variables, x2 and x3 in this case, then that means we'll always have a structure like this in the rows that correspond to these free variables. There's always this 1 entry corresponding to the free variable, because of course that needs to be taken once. And there's always a 0 for all the other free variables. So with these lines, with these rows here alone, we can see that those 2 vectors are linearly independent. And of course, they span the whole solution space. So the number of free variables corresponds to the number of linearly independent vectors that we need to span the solution space of the system. So that's always the dimension of the solution space. And as we know, rank nullity theorem, that number is equal to n, number of variables, minus the rank. That's the number of free variables, so that's the dimension of the solution space. Sorry. I hope that answers the question.
There is another question that is, can you span a solution space that contains only a point?
So if I want to span a solution space that contains only a point, then strictly speaking, if we're only speaking about homogeneous systems, then that point can only be the 0 vector. Yeah, so that's the only possible solution space of a homogeneous system that only contains 1 point. If I want to span this, then yes, there is a convention. So by convention, this is the span of the empty set. And that's also why we can say that is 0-dimensional. The empty set contains 0 vectors, so the length of that basis is 0, and we're good. Yeah, but again, that's a neat convention that just happens to fit in nicely into all the definitions.
Yeah, there is one last question that it says, is another term of a free variable a slack variable? I have to say that I've never heard about a slack variable, but it might be. Like...
No, not really. So a slack variable is an expression that you use in linear programming. Usually if you apply the simplex algorithm, there is some connection between free variables in systems linear equations and slack variables or non-slack variables, or better, basic and non-basic variables in the simplex algorithm, but it's not one-to-one. So a slack variable is not a free variable. No, please don't confuse those two.
And so far, there isn't any question more.
Okay, wonderful. So I'd say if you have any more questions, feel free to post to chat. I'll have a look at those later on and see if I can answer at least some of those. And of course, feel free to answer for yourselves if you know the answer. Otherwise, sorry.
Yeah, there is a question that it says, do we have a page or something like that where I can find the most important formulas, as I feel like that I am missing formulas when I'm trying to solve the homework? I think it might be that it's related, I'm not sure, but I guess it's related to the formula of solving the parabola.
Solving the quadratic equation. So I really hope you learned how to solve quadratic equations in school. Yeah. If you don't, I suggest I guess Wikipedia would have a good explanation of that. So those basic formulas are often explained quite well on Wikipedia. It doesn't make much sense to refer to a math book for those, I guess. Of course, there are loads of collections of different formula, but I don't find those very useful. So basically, there's 2 handfuls of formulas that you should know, and this is one of them, obviously. And that's all you're going to need.
Yeah. Okay, that's all.
Okay, great. So again, thanks, Asuri, for moderating the chat today. Thank you for participating and asking questions. If you have any more, feel free to post the chat. And otherwise, I'll see you next Monday or in the tutorials on Thursday. So goodbye.